ladies and gentlemen. Great pleasure to introduce Professor Zharkova, who grew up and studied and graduated in Kiev, in the Ukraine, during a time when the Berlin Wall was still standing and the Iron Wall was still there and we had a Cold War. So she knows a lot about what you're allowed to say and what you're not allowed to say. I hope you remember not to say anything that might put you in our... but she graduated in 1975 with a BSc in applied mathematics physics. She did her PhD in astrophysics on solar theory. She moved to Britain in the early 90s.
1992, yeah.
First in Glasgow, where she worked at Glasgow University until 1999, and then in 2013 joined Northumbria University as a professor in mathematics.
Yeah, but in 2000 I was in Bradford for 15 years.
Okay. So her research into solar magnetic fields was widely reported a few years ago when you gave a presentation at the Royal Astronomical Society, which is when we noticed your research. And interestingly, some climate scientists weren't very happy that you did research on these issues and not happy about your findings, and actually tried to tell the Royal Society not to
withdraw.
Yeah, withdraw basically, which is
press release.
Reminded you of Ukraine, I guess.
Yeah, but I'm tough cookie, so no way.
No, the research is very interesting because that's how science should work. You research a field, you make a prediction, and then you wait and test the prediction. And that's exactly what Professor Zharkova has done. She is predicting a significant decrease in solar activity and with testable, empirical, observational results. And we will have to wait and see what this solar activity or inactivity or decreased activity will do in coming years. No one knows. And Professor Zharkova has said she doesn't know what it will actually do to the terrestrial climate because no one really knows what's going to happen in the next 10, 20, 30 years. And Professor Zharkova, it's all over to you to explain how you came to your findings.
Thank you very much. My great honor to speak in this very respected audience. Thank you very much for inviting me. Just to remind me that I had also press release in 1998 when we discovered sunquakes. Maybe some of you heard in May 1998 they were also in all the news. So I'm not that, person who keep hiding. We always find something which no one else looked, because you look in and you're doing it. So anyway, this came up, what I will be speaking today, came up unexpectedly, and I will explain you why we get there. So this is plan of my talk. I will speak about motivation, sun and solar cycle, and sunspot, bring you to the point sunspot and solar background field. And then I will, from principal component, I will speak about my research. So why I will be, point. So you've probably seen these talks many times about sunspot. Sunspots were discovered probably first month when they invented the telescope, and they immediately put the drawing and found these dark spots on the sun. And they put this drawing onto the paper and started investigating the sunspots. But it turned out that even 28 BC, Chinese also observed sunspot, although they didn't have exactly data available fully. So how sunspot look like? This is the real sun of the modern instrument. As you see, orange sun because the photosphere has average temperature about 6,000 Kelvin. These are dark spots, sunspots. So in enlargement, they look like this. They have coming in pair, leading polarity, trailing polarity. They normally occur on the solar surface on this about 2 weeks until they rotate and go from the opposite side. So these are sunspots. Of course, they are very nice and very bright features. At that time, they couldn't see anything. It was only first the telescope, and they took about a couple of hundred, maybe 300 years until Schwabe discovered that actually sunspot, he started counting the sunspot and discovered they appear actually in kind of cycle. So he first discovered the cycle, and after him, Rudolf Wolf actually realized that probably this is daily observation. They could be organized, and we can put this solar activity of sunspot with some average sunspot number, and this is how this sunspot thing started. They started using sunspot as the measure of sunspot of solar activity, and Carrington, he discovered 1858 that when he looked at where sunspot occurred, they see that at the beginning of cycle, sunspot occur at the higher latitude, so-called royal zone, and then migrate towards the equator, and toward the next minimum, all the sunspot finished near the equator, and then no sunspot, and new cycle starts. So Maunder eventually built this diagram, and oops, what I did? Yeah, here. Maunder built this butterfly diagram, and this is what is modern solar activity. So you see, this is the average sunspot number, which I gathered from all the observatories around the world, averaged dramatically over all the observers and potential cavities. And these are mounted butterfly diagrams, which show how they vary, so every single cycle. So this is the cycle 23, which finished, and this been used for characterization of solar activity. Why we needed to characterize solar activity? Eugene Parker came up that because the solar dynamo, magnetic field in the sun, so during the minimum, you have, for example, north on the north hemisphere, south on the south hemisphere. Then you have poloidal field, background magnetic field coming through the whole sun, but then the sun starts rotating. During the maximum, the polarity starts changes, so very often the polarity changes during maximum, and you might see that sometimes a couple of years they have similar polarity during the maximum north and south, and then eventually they fully change polarity. So this is dynamo in action. This is why the number of sunspot varies. So how they vary? So this poloidal field, which is background magnetic field, is changed because the sun rotates differentially, so equator rotates quicker. So these magnetic field lines keep getting on the equator and start twisting, and they form the sunspot. So the sunspot is toroidal magnetic field, and this is this poloidal background magnetic field. And so exchanging one field to another, this how solar activity works, and makes sun, producing sunspot and active region, and so on. So everything perfect. Very nice. Then we started doing the coronal observations in 80s, and discovered that indeed not only sunspot number increases with solar activity, but also increases solar corona, becomes much more active. First it is no bright points, and this is corona in the soft X-ray, become very dramatically bright in soft X-ray and hard X-ray during the maxima. So this is put everything in perspective. Indeed, solar cycle works fine. But So what is the interesting point? This is 400 observation of solar cycle. This is average solar activity, and we see the immediately when they built, they discovered, yes, solar cycle could be very different. You could have minimum solar activity, and suddenly they put up, there was about 50 years, there was no practically solar activity. Something happened to the sun. So what this affect? Why we should be bothered? We should be bothered because Jack Eddy, when he looked at the temperature variations during this period when he had found the minimum, he discovered that the temperature also decreased very dramatically. So from the Jack Eddy's spot, they suddenly started linking the temperature of the Earth with the cycle of solar activity, and so the decrease of solar activity will lead to the lower terrestrial temperature. So they put, indeed, this is the solar activity for last 400 years, and this is the temperature, and it looks like that more or less like, not exactly that very dramatically drop, but smaller, definitely smaller temperature. Plus, what you can see that there are a few other mechanisms which affect solar cycle or what affect our temperature. Not only radiation which come in from the quiet sun, from the orange sun, but also which come from UV radiation, which Solanki and others, they discovered UV gives you very big number of radiation. And then they discovered the opposite force which acting on the temperature, cosmic rays, which always when you have minimum solar activity, you have maximum of the cosmic rays. So this is UV radiance, which is actually higher energy radiance, which comes very dramatically. Of course, our atmosphere mostly protects us from it, thanks, but not always. If you have ozone holes, this UV radiation comes to big cities, there were the holes, so we can completely ignore it. We have to pay attention. And plus, this is what happened with the cosmic rays. It was found that during the minima solar activity, cosmic rays maximal. So something like if you have minimal solar activity, magnetic field of the sun become lower. So it allows the cosmic strangers to precipitate, to bombard the Earth's atmosphere, not only Earth, all planets, because sun protects whole solar system. So this is like more or less picture why we need to know solar activity. But do we know it? We know that it has magnetic field. This is sunspot, how they look like. They actually flux loop, where the flux loop are embedded into the atmosphere. What become problem with this picture, which I brought you, that when you start predicting the solar activity, so this magnetic field in the sunspot, which Parker predicted, that magnetic field of the sun is converted to magnetic field of these flux tubes, toroidal field, and backwards, looks very fine. So if the theory is okay, then we can predict what will be, how many sunspots will be the next solar cycle. So they couldn't predict, they tried to predict, not enough, but we came to the modern era, and this is how I got into this field. I was doing European grid of solar observation again. Done something wrong. Keep pressing. We done the catalog. Sorry. We done European project for 3 years, and our task was to detect sunspots on the surface with maximum accuracy. Whatever you can build, you detect. So we did it. We built sunspot catalog, we built active region catalog, we built filament catalog, we put them everything together. They look very nice. So we could, this is what we do. these are features, active regions in here. We can overplot one feature on another. For any time, this is cycle 23, these are filaments. We can overplot them. And we can put sunspots as well. And we can give you even enlargement. So we have everything data we could. We use the data to predict solar activity. And we still cannot get proper prediction. We couldn't get something. So these are catalogs which published on the website. You can go. But we couldn't. All these improvements did not succeed in prediction of solar cycle. So we're doing something not what we should be doing. We're probably looking not in the right direction. We're missing something, some clues. So what we're missing, some clues. At that time, what happened in 70s, they discovered magnetograph, and they started building full disk magnetograms of the sun. And this is full disk from Wilson Observatory. We use Wilcox Observatory at Stanford. And this is magnetic field of the sun, not sunspot now. You take full disk magnetogram, and you build this magnetogram against latitude, northern latitude and southern latitude along the years from 75 to 2010. And what you discover? You discover that this magnetic field actually follows similar pattern with butterflies. But we also discovered that this, remember magnetic field leaking towards the poles when changing polarity? This is when it starts, when the maximum solar activity is leaking to the next polarity, okay? We look, at that time, we luckily had all the data. We had all the sunspot data, and we got this data from magnetograms from the sun for 3 years. So we decided to compare this data. So this is the magnetic field in sunspots, negative polarity, positive polarity. Obviously, this is leading polarity of sunspot. This is magnetic field of background. It is obvious that background has opposite polarity than the leading polarity. So what it says, that background actually has the upper hand, which allows sunspot appear on the surface and migrate, but not sunspots. So like sunspot are little kids which follow big mommy, which is great sun, and they follow in this direction. So the period of difference of this, come back, period about half solar cycle, 11 years. So we normally get solar cycle is 22 years when the polarity changes fully from north to north. So what we thought, yes, we're missing something. And we started thinking, let's see what we're missing, like in detective story. So let's remind how people did. This is the white light. Remember, of course we don't remember, but we remember the history, that when you put white light onto the prism with equal sides, triangular, because of different refraction coefficient, white light suddenly become actually different wavelengths. So Richard of York, we have rainbow, gave a bottle in wine, yeah? Something like that. So it means that in front, the white light is not exactly, doesn't have characteristic wavelengths, it's white light. But when you put through the prism, this light has wavelengths of UV, this light has wavelengths of red light. So we now can convert this set of different wavelengths into separate one and prescribe them wavelengths and amplitude and everything. We thought, can we do this with magnetic field? Maybe magnetic field does the same. Maybe it has number of magnetic components in it. What can we do? The only thing which can separate this magnetic field is principal component analysis. So you put the whole solar magnetic data, and principal component analysis, you run eigenvalues on oscillations of the sun. It runs very nicely. It's very strict mathematical method. It is not approximate method, as you know. So we've done this. As soon as you run it, you will get component 1, component 2, component 3, this is what we suspected. And if we were right, yes, we did. We built so-called spree diagram, which is eigenvalue versus variance. We sorted our eigenvectors by their variance. So how much data are responsible for this vector? And look what we discovered. We discovered that my eigenvectors of solar magnetic field came in pairs. One pair, two principal components, with the total variance about 39%. It is variance, it is sigma squared. If you get square root of 39, you get about 67%. So these are, we later discovered, these are exactly magnetic waves which are responsible for the dipole magnetic waves. Waves induced by magnetic dipole on the sun. Then you have another pair, quadruple, another pair, sextuple, and so on. So at that time when we discovered, we didn't realize there will be dipole, quadruple, we just got pairs. Nobody knew that waves come in pairs. In all theories, they always produce one dynamo wave. And suddenly we got two of them. So this is what we got. 2012, we got these waves, and waves behave very peculiar. One wave starts opposite polarity from southern hemisphere, it still moves to the north. Another starts from the north and moves to the higher latitude. And at some stage, they got equal amplitude, they got into resonance, and this is where maximum solar activity starts. Then the waves somehow separate, and they start moving toward the southern hemisphere. So this is given that northern hemisphere become more active, and this is cycle 21. Then they move to another hemisphere, the southern hemisphere become active, and you see if the peaks of these waves are separated enough, you have two double maxima, which Gnevishev law, it is shown. It comes up very easily from principal components. So this is cycle 23. This is historical data which we used to discover this curve, and these are, we predicted. This we used how they behave, and then we calculated for another cycle 24, 25, 26. But when we predicted, we didn't know what does it mean. So I produce magnetic field, you ask me, and what? You like it field? Well, fine. So what we did, we discovered that this field, if you put this into special software called Eureka, special method using symbolic regression with Hamiltonian approach, this is the software which is free for the university. If you walk through the university, everyone can repeat it. So if you put into this software these principal components, this software discovers your analytical expression for my curves, which I never do with the full magnetic field. You put full magnetic field, the software crashes. But when I put these clean, nice components, it gives me two components. And look at that. It's combination of five cosine functions, but combination of the product of five cosine functions. And look at that cosine of cosine. So no wonder that they try to predict solar cycle 24 with 150 attempts to predict this cycle. Only two predicted that it will be lower than cycle 23. 148 did not even were close. So because they always think that the only wave you have is cosine, single cosine. No one thought there will be cosine by cosine of cosine. So this tells you, something, we got something into it, but we still don't know what we got. So we got nice expression. So what we decided to do, we decided first check our formula. We put, this is the curve which we got in 2012. Then we put into Eureka and predict the cycle 24, which is the solid curve. And the dash curve is what measured, because while we were doing this, it was not like that. It took a while, couple of years. The cycle was progressed. We were at this point when we compared, and we discovered, yeah, look, formula gives us very pretty close fit. Look at that. Really, we found 97% actually fit. Wow. We were really impressed. So what we wanted to make sense, what is going on here? Because while we were proving this to the referee wanted, you done it. You know, when you got these formulas, they can't believe it. That from 3 cycles, you suddenly got formula. I said, look, it obviously proves that the sun is very stable oscillator. So it doesn't matter how many cycles. We tried for the referee from one cycle, from a couple of cycles in different combinations, we still got the same result. So look, the sun has very stable oscillation. So what we decided to do, we decided if we have 2 waves, we never work with 2 waves. We always need to put them interference and produce summary wave. So we produce the summary curve, a standard ification, and look at that. So what we got, oops, as always, we got this here. Summary curve started behaving more like closer to sunspot numbers. But what we discovered that my summary curve was higher at cycle 21, then lower cycle 22. Again, lower cycle 23, it will be much lower cycle 24. And what is something happened in cycle 25 and 26? Wow! So this curve is also show the same nice correspondence to our formula. But now we don't have artificial intelligence data, we have formula. So we can calculate as long as we wish, as long as computer could run, we can calculate as many years we want. But we wanted to understand what it means. What? Again, the referee started asking, what does it mean? We said, oh, what does it mean? Do you like more sunspots? Yeah. Okay, we make it for you, they look like sunspots. Let's put this negative magnetic field, which is real negative, to transformation modulus. Reflect it all to the top. This is what we did. Referee asked it, we did. This is our curve. And this is average sunspot number. Look how nicely they fit, especially cycle 21 and 22. You thank referee that he was very stubborn, but we turn out to be more stubborn. Even cycle 23, you see this, the observation comes to be higher than our curve, but it turned out this is because in Locarno, Sergio's Carcasi multiple by factor 3 all the sunspot numbers, so they now reduce this number which fits our curve. So what we said that our curve, actually summary curve, reflects solar activity with much less pain, because I don't need to combine with every observer and every observatory, with every whatever they have, weather condition or whatever. You can get magnetic field, we're actually using synoptic maps in every observatory, and they come with the same, approximately the same curves, more or less. So we said now, if we have this curve, maybe our summary curve, modulus summary curve, tell us a little bit more about solar activity on the language which people used to have about average sunspot number. Say, okay, this is average sunspot number cycle 21, 22, 23. This is cycle 24. Actually, we are the only one who predicted this maximum. No one even looked at it. And look what happened in cycle 24, 25, slightly lower than 24, but cycle 26 drops by order of magnitude. So remember, these waves moved into opposite hemispheres. They stop interacting. So something going on, the activity is dropping very dramatically. This is what we found, but remember we found it because we have the formula. We thought, okay, it's only 6 cycles. Why don't we now calculate this formula? So we prove actually our formula with naked eye observations in these 13th, 14th centuries. And their actual observation fit pretty well what we predicted, strangely enough. So it gives like, it's not everything perfect. I will tell you errors which we had, because we use only dipole magnetic field wave produced by dipoles. But what we did, we ran our calculations by 1,200 years forward, up to 3,200, and 800 years backwards. And this is what we got. This is these 3 cycles which we used, and this is the curve which we got from these formulas, which we got, what we suddenly discovered. Boom, 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 boom. Here we got mountain minimum. Right, it looks like we have extra grand cycle. These are smaller cycles, and this is envelope cycle, which about 350 to 400 years, and between them we have grand minima. And grand minima in mountain minimum was pretty long one, but the upcoming, we've seen this decreasing, so we have upcoming grand minimum upon us. It is literally within, in 2015 it was 5 years to wait. So whatever critics keep telling me, I said, okay, maybe you're right, maybe I'm right. So it is not long to wait. The sun will decide very shortly. Just stop dividing. This was nice. Of course, they discovered that our Dalton minimum was not shown here. It should be Dalton, and we don't have Dalton minimum. I'll tell you, we repaired this. We produced another paper. But what is nice, what is found that we have this like envelope type of oscillations, and this is, at that time, I just started teaching my students waves, and I taught exactly today this effect. When you have 2 waves with the close frequencies, they produce this kind of oscillations they call beating effect. You know, beating effect, when your piano guy comes to tune it, he put the forks and counts number of the beats to increase the tension. So, of course, on the sun we don't have anyone to tune the fork. So it has beating effect, clear beating effect. So what we now see that these 2 waves should be occurring into different layers, and when they travel from the interior to the surface, they interfere and they produce this beating effect. It becomes very beautiful, like a demonstration of the waves. So what we did, what is interesting also, if you look at this, not only mountain minimum were predicted, this is the Wolf minimum. And I'll give you further calculation about back 3,000 and 5,000 years, all minima, including Homer minimum during the Roman Empire, we managed to predict. So dynamo, we got this, and so far we didn't touch dynamo at all, no theory. Everything we did was from observations, from principal component analysis, and from this formula we produced. But we wanted to understand how this wave would be shown in dynamo. Can we reproduce this strange wave, cosine of cosine and product of cosines? So we invite Elena Popova, young scientist from Moscow. She just graduated with her PhD. So she was open to new suggestions, because I spoke to every single scientist who does dynamo, and they were terrified. 2 waves. We don't know what to do. Or just go. We do this thing. We got funding for this one. They put the sun parallelepiped. I said, have you seen the sun parallelepiped? We always see sun, the sphere. No, the model parallelepiped. I say, okay. If you like modern parallelepiped, continue modern parallelepiped. We go to this simple sun. So we used, what she used, she actually looked at the Parker model of dynamo, used 2 layers with meridional circulation, V, and normal alpha and omega effect. So basically what we used that standard dynamo model with alpha and omega effect, but we put also meridional circulation in 2 different layers. So there were 2 layers in one hemisphere and 2 layers in another hemisphere. Produced the model. We published 2013 at the same time with the guys who built HMI instrument SDO. They discovered these 2 layers from helioseismology. So we came independently. We didn't know they will find. Our paper already was published, and again, referee tried to crucify. What are you speaking? Where are these 2 layers? No one see them. I said, we didn't see because we didn't have instruments, and suddenly Zhao seen it. They seen it in SDO, then they seen it in GON, ground-based instruments. So suddenly we become singing in unison. So Popova managed to reproduce she selected particular parameters. She reproduced this poloidal field, reproducing this being, of course it is not ideal, it doesn't show things, but it shows this. You see that it is higher amplitudes and narrower cycle. This is wider cycle, this is expanded cycle. So she managed to reproduce, to find some dynamo waves, which general, the phase view, reproduce nicely what we observed. And we managed to get even these nice grand minima between them, because we, in the paper Nature Scientific Reports, we show how the difference must be between the frequencies. Difference very small. What discovered that in these 2 layers, the difference in the circulation, meridional circulation, only 1 meter per second produces you this beating effect. Wow. Only 1 meter per second. So the sun is very fine-tuned instrument. Someone tuned it very properly and it acts properly. But remember, we look at this, we had another more components, and we look at our early paper, even before we got the analytical formula. This was dipoles which we have, but then we have 2 quadruples, 6 tuples, and other things. We thought, oh, maybe if we add at least quadruple, we can recover Dalton minimum, because it was not shown there. So this is what we did. We basically, we couldn't do analytical, we didn't have time to derive it from the formula, but we added it from the theory. We know how quadruple wave look like. So we said, let's have quadruple wave with a period about 100 years. And we add to all our 2 dipole waves, which we have components. When you add them, you suddenly get very nice curve. So this was Wolf number, which I get from my summary curve without Dalton minimum. It didn't occur here. And when we added quadruple component, here is my Dalton minimum. And here's another 1900 millennium. So we managed to recover these centennial cycles as well. So if we keep adding, like in white light, so we use UV, then we added blue, so we need to add another few lines, and then we get, probably eventually we arrive to what they observe in magnetic field. So this is nice. And then when you recover, so this is my previous curve when we didn't have Dalton minimum, and this is curve corrected. Here is a Dalton minimum, and here is another one in 100 years. So this was one of the objections of those people who run with the sunspot, because they resist with all their fibers. They don't like that we are using some other proxy. I said, look, this proxy has much less errors because it doesn't depend on the seeing by one of instrument or another. Sometimes they see less sunspot, not because they're less on the sun, because the seeing in this particular ground-based observatory is worse. So it was difficult, but nonetheless, by doing this, we now can look at the back on the mount the minimum. So I want to get back what I saw, that during mount the minimum, the temperature dropped. So what we looked, what happened mount the minimum, Lin et al. I think, no, here. Lin et al., they did this restoration from biological things, and they discovered the temperature dropped, but only 0.1%. So definitely this temperature probably could not account for the full temperature decrease which happened during the mount the minimum. This is the temperature decrease in England. So temperature decrease was about 1.3 degrees, and it was freezing, Thames, snowing and everything. So in the current climate models, they use only irradiance as the forcing term from the sun. What we were saying, because we now work with the magnetic field, we're saying that probably you're missing the main contributor. You're missing the magnetic field. Because magnetic field is basically producing the shield to the whole solar system, and if upcoming mount minimum, we first called it mount the minimum, but it is not mount, it is modern minimum. It come in 2020, 2053. 2020 is around there. We can see it right there. So basically, this temperature will be decreasing, and because magnetic field decreasing, and remember the cosmic rays. If magnetic field decreasing, suddenly we will have much more cosmic rays which break the clouds and cool off the atmosphere. So if we have greenhouse, there are two ways to cool greenhouse. Stop heating, what climate people, IPCC say, or you open the window and put the heat off. And this is what sun does. By reducing the temperature, reducing magnetic field, sun literally allows all the cosmic strangers get to all the planets, break the clouds and allow all the heating come off. And as you know, I don't know if you've seen it, but there were, when we had maximum heating in the Earth, there were melting ice in Mars and typhoon in Jupiter. So obviously it cannot occur, we cannot do this. Even if we heat our Earth, we can still heat even Mars, despite it is close to us. And definitely not Jupiter, it has to be only Sun who does it. So anyway, so we now at the point that we waiting for the grand minimum, and we expect that the temperature would decrease, but how much it is decreased, we don't know yet, but there are very nice now, our work inspired the whole cohort of scientists who started doing new simulations, including different. And this year in Portugal, they met all the climatologists from the Earth. They started investigating all these effects, and they sent me links to their papers. I'm not climatologist, I'm solar physicist, but I'm really impressed how they describe that, how the temperature would decrease. So anyway, we done prediction now 2000, which was, okay, I'm back. We done prediction with 3,000 and 10,000 years. And what we discover that modern grand minimum upon us, and I want to speak why it is important. It's not only scientific importance for us. It is, first of all, of course, scientific event will be literally astronomy walks into each house. So you like it or not, but you will see it. But other is solar terrestrial events. So you can check pros and cons of solar dynamo, but these big impacts will be on the terrestrial temperature, reduction magnetic field. What it says, remember we had snow in April last spring, and all crops with potato in the north, literally, and some other crops, completely washed out. They needed to put end of April, beginning of May, new crops, and this will be repeating. So when it comes towards the to 2028, will be minimum of cycle 26. It will be 2030, 2031. Around this time, we will have very severe weather. And what we need to think, not about the increase of the temperature. At that time, the temperature will be decreasing. So the governments in each country need to create the stock of food which can distribute to people. And they can have not only to people, to animals. Because, okay, you have cold, you get into your house, it's warm. But if there is no food, you need to get. If they cannot feed animals, they would need to kill them. So 1 year you have a lot of animals, other you don't have them at all. So this is what need indeed intergovernment efforts for the next 30 years to support nations. It will not be overheating, it will be overcooling. And so terrestrial temperature in the past, this is the temperature variations which come. It turned out that the temperature indeed increasing, this is the minimum, temperature increasing but not straightforward, it's increasing like oscillations. IPCC, they use this interpolation, and Akasofo has shown this. This is simply wrong. So this is oscillatory function. They put linear interpolation and got 3 degrees increase. So it is not possible. This was published 2010, 2011. So after that, after we published, they reduced. The published paper 2016, they reduced the temperature by 2 degrees, but they still insist in the wall. But what we see, the temperature still increasing in here. And what we looked, now we have the computer. I will come run quickly. Will the temperature indeed be increasing? And what will be happening? So this will be a grand minimum which we need to think. And then maybe beyond our life of our children, will be still temperature increasing? And will be increasing because of us or because of the sun? So what we said, we have this, I said, computer, we have formula, we run it for a couple of, actually 3 weeks, and we got very nice curve. This is our summary curves for 100,000 years. So 100,000 years, you see what we discovered, that apart from grand cycle, we have super grand cycle. And we couldn't understand, from dynamo point of view, we can't emulate the super grand cycle. So we now depart from the grand minimum. It will be there, but what will be happening with the sun? So what we look at this, we suppress the oscillations of the normal solar cycle and look at the oscillations of the baseline. So this is 0 line actually. It is not stable. It just oscillates like this. And oscillation of the 0 line is exactly 2,100 years. And you see how nicely this cycle for 100,000 years, you imagine how many cycles we get there. So what this comes from? Not from dynamo, not at all. We couldn't find anything in dynamo which could fit this. So we put this closest oscillation, the closest 2,000-year cycle, and we found that actually its minimum was during the minimum. And this baseline started increasing magnetic field exactly towards, it will be increasing for 2,600. So rings the bell, why this was during the minimum was minimal? It probably has to be related to solar irradiance somehow. So we used the curve by Solanki, who restored solar irradiance. We produced this curve on top of and we discovered indeed the irradiance follows our curve. So it means that the oscillations of this baseline exactly says that irradiance keep increasing. And it looks like it will be increasing for the next 500 years, independently, whether we crawl into the caves and stop producing any heating or not. And this probably will do with this irradiance. Why? Again, you got puzzled, you start digging all the literature, everything. We look at this Milankovitch cycle, we look at what sun is the center of the solar system, all the planets, and we found the answer. It turned out that Milankovitch look at very nicely. We cannot be avoid that we're part of the solar system, we're part of celestial body. So if you put the sun, it turned out it has solar inertial motion. The sun motion is affected by large planets, so the sun basically moves around barycenter, center of mass of Earth's sun system. And sun radius is 696 10 to 5 kilometer, but this radius is about 4 radius of sun. So if you put, this is how sun runs. It runs, this is red, 4 radius, 1, 2, 3, 4. What is happening? The sun moves either closer to the apohelium of the Earth or closer to perihelium of the Earth. And what it means, I skip this one, we look at the weather. So if sun moves closer to perihelium, this is our Earth in July, it means that we have hotter summer in the northern hemisphere and hotter winter in the southern hemisphere, but we have colder winter in the northern hemisphere and colder summer in the southern hemisphere. If sun keeps moving, and at the moment we discovered it keeps moving because its baseline moves up to the northern hemisphere, so sun keeps moving to the apohelium, the temperature will be increasing, and it was increasing. During Roman Empire, they found that had grapes in Scotland, close to the Shetland Islands. It was hot enough. So obviously it is not that rare, and this occurred, if you look for 100,000 years, many times, and the Earth's system with sun survived this many times. So this is what basically what we discovered, and what we were saying, that increase of the temperature will exist after this grand minimum. So we need to survive grand minimum. Maybe not us, our children, they will go through this increase in temperature. It will be summer, nice summers in Great Britain many times. And as I explained, and nothing to do, I don't know if there's finishing, I'm nearly there. So even if humans do not put anything, as we all crawl to the caves, the temperature still will be increasing. This is the main thing. And this is what we try to say, that planets, this oscillation of the baseline is part which is in feedback of the solar system onto the sun. So everything we see, we can avoid, we're part of the bigger system. We see something which is not coming only from us, it's coming from sun, from other planets, and we have to respect them. So this is basically it. And thank you very much.
My first question before I open is, so you're actually making a clear, based on your research findings, a clear prediction saying that after 2020 temperatures will begin to decrease.
Decrease, yeah. It will be.
Have you found anyone else among your colleagues who would be sympathetic to that kind of prediction? Because from...
Oh, we found, yeah, we now have a couple of dynamo people. Matsumi Dikpati from Boulder is with us, and so they started warming up, because basically we don't involve parallelepiped of the sun. We're still using the round sun, and we.
Because you were, if I may, you were much more cautious in the past with what the effect of the decrease in solar activity would be on the terrestrial climate. You were much more careful in these.
No, I was saying it will be decrease of the temperature as it was during the minimum. So when they start striking on you, they want to crucify you, put into the wall and say, put the rifle and kill. You say, okay, I'm not saying you do anything you want with your temperature, but within 5 years, in 2015, the sun will show us who is right, either me or you. And then we will see who will be killing whom. So this is the thing. So you have to be diplomatic when you put something. And I always say, some colleagues don't like this, what I say, but I say, look, when we had during the minimum, always the change of the system. Remember, at that time, it was Ptolemaic system, that the sun rotates around the earth, and earth is flat and everything, and the planets rotate around the earth as well, and they needed to invent two spheres, the planets should jump from one to another. They were very, very inventive with this sphere. Suddenly, Copernicus came up and said, no, we don't need it. We just put this sun in the center, put this geometric progression, put around the planets, voila, you got the system. 16 years this theory existed, and they refused to accept it. 16 years, until Kepler calculated this theory. At that time, remember, Giordano Bruno was burned in the fire, and Galileo said, no, I don't want to see. So I tried to act as Galileo. I didn't want to get burned.
Okay. But basically, within the next 5 to 10 years, we surely will see where the temperature trend goes. And of course, the IPCC makes the opposite prediction. They are claiming or predicting that temperatures will increase by 0.5 degree by 2030. So there is a clear upward trend in there.
And you will witness it within 10 years. Who is right?
Good, excellent.
And this is it.
Proxy data, I think, shows that the previous 5 warm periods have all been warmer than the present one.
Yeah.
Now, either that means that in terms of effect of the sun on the Earth has changed in other ways, which reflects that. Or
this, you have to be careful here. So what is trending, the variation of the baseline is very small. It's about plus minus 10 units.
Sure.
But the variation of the solar cycle is plus minus few hundred units. So the variation of this solar activity, this what will happen. You see, this cycle was stronger than before. This is the single cycle. This is part which comes from dynamo. Something happened inside the solar interior which encourages larger cycles. So conditions were such that dynamo amplitude was higher.
Yeah, I'm making a rather different point. The whole of this analysis depends on the principal component analysis, and over a very short period. Now, if you take 100,000 years, you're into the Milankovitch cycles.
Yeah.
So this is a set of cycles which don't reflect Milankovitch. They're only reflecting short-term variations, and that you have to impose the Milankovitch cycles on top. So it could mean that if you'd taken a wider set of data, you might have got another another term in the equation, or you may have found that some of the constants were buried a little bit. And so you'd make the other predictions. So either you'd predict that the Roman warm period was warmer than us, all other things being equal,
they hit the right day.
Or you'd say that because of us wobbling around, the changes in orbit and so on of the Earth, whether it's circular, whatever it is, at the time, that was the reason. But you can't have it both ways. You can't have your cake and eat it. So
No, I can't.
I suspect,
This is the beauty of it.
I suspect that there are small nuances in the equation, which this is good enough. It's good enough for the prediction you've made, but I'm just wondering whether, you were talking to Tolbert just before, he would argue that the changes in the dynamo effect are gravitational in origin, and they're to do with the alignment of the planets.
Yeah, bring you
And
back
those alignments are going to change significantly over a longer time period.
to
than
this
you
curve
predicted
in
till now.
here, what I put here. When you look at these 3 cycles, so when we did simulations, and the very first one with this one in here,
Yeah.
we done the calculation of the parameters for each single cycle, and they come nearly the same coefficients. We combine them in pairs, they came with the same numbers.
Yeah.
We get all 3, you got the same number. What I'm saying, the sun dynamo is very stable oscillator.
Yes.
So obviously it does matter how you combine how many cycles. If you have a stable oscillator, you'll get its parameters immediately from single cycle, and it progresses well. What it says here, that we can explain why we have these grand minima because of the beating effect of these 2 waves. So this is what came up unexpectedly, because it came up that the frequency of these 2 waves were not equal, but very close. And this is what you produce, these beating effects, which keep
Okay.
repeating every 1, 2, 3, 4, 5. This pattern repeats every 100,000 years.
Do you think that this is internal, or is it caused by the externalities of the motion of the planets?
No, it is. This is produced. This is internal. This is dynamo. This we reproduce by dynamo waves. So this is what
So there's a
we
fundamental,
managed to produce. This what dynamo waves. So
there's a fundamental difference here, that some people feel that the perturbations of the dynamo effect are gravitational, and you don't think that's the case.
no, it is the case. The gravitation perturbate the 0 line. So this 0 line is not state. What I was showing that planets make it also oscillate with this 2,000 years. So in this particular cycle, there was it was Mount the minimum. So it was minimum here, and then it started increasing. It will be maximum in 500 years and will be decreasing. But it will be slightly, this 0 line will come up. This effect of planets. But this is effect of the sun itself. This is happening on the sun.
I'll leave it to Tallboy.
Okay,
Okay.
please.
I mean, you've identified the period around 2,000 years,
Yeah.
which is commonly known as the Hallstatt period.
Yep.
There's another one that was found by Paul D. Jose in 1965 called the Jose cycle, which is 179 years.
Mm-hmm.
If you take the sideband harmonic of the 179 year and turn that into a beat period with the Hallstatt, then you get a 208 year cycle, which is strongly evidenced in the 10 beryllium data, which we is used as a solar proxy. And that 208 year cycle is well known as the De Vries cycle.
Yes.
So we would contend that as well as the 2,000 year cycle you've identified, there are other important cycles in solar activity
Oh yeah, there will
that
be.
also relate to other planetary orbital
Absolutely, there will
periods
be, because-
and the harmonic interaction, resonant,
Let me remind you
the
that
orbital resonant interactions between them.
this
So-
curve was without the quadruple component. When I had quadruple component, I got this Dalton minimum. So if you put, this is 100 years,
Yeah.
and when you put them together, this you get your 179, because
Right.
it's not always 100, it's sometimes 90 years, sometimes
Yeah.
this is,
So that's the
this
Gleisberg.
quadruple component comes out.
That's the
It
Gleisberg
will-
period.
It was another,
Yeah.
yeah, exactly.
Yeah.
So we done on the beginning, we couldn't do everything. We done dipoles, and we found how we can repair the quadruple. So in the future, if I have enough life,
Let's
or
collaborate.
we collaborate, we can do, or we'll teach younger people, let them do it. As soon as we got this idea, it's not very
I
difficult.
mean, what's really exciting is that your results from the internal magnetic oscillations
Yeah.
that you've discovered and our output from our planetary model are almost identical.
Exactly.
They're almost identical. I'm going to give you a copy of the paper later on, but it's quite amazing that we've come from a completely different approach
Yeah.
and yet have a model output that's so similar to your model output
Mm-hmm.
that it's almost saying there's some kind of linkage going on. here
Very
between-
likely, the condition on this outer layer is affected by the planet. So
Yes.
dynamo conditions in this outer layer,
Yeah,
alpha and omega effect,
yeah,
are induced by the planet. This is why they have this specific frequency.
Yeah.
Well, everything which happen in the bottom of the tachocline is produced by solar dynamo. So this planet, solar dynamo, they interact,
yeah.
and on the surface you have the result. So we can't avoid, we live with the neighbors, we live with the neighbor's sun, neighbor the planets, we have to be very nice to them. Yes.
Okay, there's another question.
Would you often mind putting a slide showing those different formulations that you have arrived at?
Well, the cosines.
Yes, cosines.
Oh, okay,
Yes.
just a sec. Yeah.
Now, this is the start of it. As I understand it from your question, when you've got this equation, what was the basis that you have used? What was the database that you have used to arrive at these things?
We got principal component. We got this clear data which responsible only for dipole. So this is, we got only principal components. So we got rid of any quadruples of anything. We got just UV line, UV spectral line. As soon as we got UV spectral line, this software, Schmidt and Lipton, they published paper in Science. They developed this software. It is available freely for all the scientists. As soon as you tell the scientists, they give you can download and you can start working with it. Any curve you have, if you nicely get rid of any extra components, you can extract analytical function. The guy who helped start doing this, Shepard from Bradford, he was doing this for medical units. And then when I gave him my principal component, I said, let's try to do it. This is what we started doing and we got it.
No, I'm sorry. What I'm saying, to this system, the computer software, you put certain data.
Yes,
Now,
this data.
all your argument is based on the accuracy.
We
or
put this
otherwise
data.
of- Yes. If you go back to the cause equation,
Okay.
now all your arguments are based on this particular equation. Is that
Yeah.
correct?
Yeah.
Right.
And all the coefficients, we derive the coefficient, have number. As soon as we publish all the results, I make this coefficient public.
That's perfect. Now, to get to that, you have used certain data. Now, the question I understood...
We use the same data which was above here. We use this data. This data. Not certain. And in the paper, Astrophysical Journal, we describe the method how you use. They very clearly describe. You can do it yourself.
I am
It's
not
very-
excuse me, I'm not questioning that. All I'm
Okay.
asking you
There's
is,
the difference.
is there any possibility that that equation might change if you use some additional part of that data?
Of course
That's
it
what
is
I'm
changed.
asking.
No, you mean if I put from different time period, you mean?
Well, whatever. I mean, I'm sorry, I'm completely alien to the subject, so therefore I'm just looking from the logical point of view. That is your start of your result, which I hope it is absolutely correct, incidentally. Don't take me wrong. Now, all I'm asking is there anything that will change that particular equation if you use original data that you have?
It did change if you add quadruple components. And this we trying to add to fit my curve for solar activity to fit better what you observe. So we didn't have Dalton minima with this simple dipole component. So we needed to add quadruple. And like in white light, so we use UV, we use blue line. So we now need to add green, then yellow, and then red. So we don't have time to do it because I do teaching, administrative. I do a lot of, we publish with my PhD student another paper in Nature, completely not related to this, but related to solar flares. So doing a lot of other things. Life doesn't stop because you discovered this one. Everything you do this as an extracurriculum activity. I don't get funding for it. It is just driven by curiosity. Well, all people who collaborate with me also driven by curiosity. They're not funded, but simply we discovered, we found something which makes it easier. So if I give this coefficient, now we're working with Austria, I give them the whole array for 2000, and they have old observations in Transylvania, Germany, Austria, in German, which never been translated. So we'll feel the solar activity data from the Earth up to 0 before Christ. So, and they compare with ours, so we now working, people are encouraged to do it, because before, whatever they produce, at the time Solanke produced, so the restoration of irradiance are very peculiar. They have this stochastic, and they say sun is stochastic. What we discovered, we see stochastic appearance, but this is visible appearance, because the waves interfere and create this beating effect. But sun is very stable, as I said. Of course, when they have more data, magnetic field they measure now every cycle, so we can add cycle 24 and see if we can correct these coefficients. But from what we found, the sun such a stable oscillator that even from a single cycle, you discover the coefficients which have about difference only in second digit after the comma. So definitely it is pretty stable oscillator, which is a very good thing for us, because if sun was stochastic, as they claim, it means like a tachycardia in the heart, human being. The person is living last years before heart stops, or sun stops. What we are saying, oh no, the sun is in perfect health. Simply these waves run and they interfere, and visible thing look like it is stochastic. But sun is absolutely stable oscillator. It will survive another 5 billion years, as we expected, if we manage to survive.
I was nitpicking, but the fact
Hold on.
I'd first like to say I think it's remarkable research you've been doing.
Yeah.
My question is this, that if one were to include the increasing carbon emissions into them, would one, into a model, would one add the IPCC model to your model over the long term?
IPCC model is model of the Earth's atmosphere temperature variation affected by exchange of the water. And they never measured actually carbon, they measured evaporation of the water. And there is research by Murray Selby, you know, he claims that they cannot measure what they claim. And
I don't want to go into the IPCC now.
so in my model, we don't have terrestrial data.
But so
What I'm relying, what they observed before, so it's like a speculation, because we don't simulate the terrestrial model.
But you have to understand that the Maunder minimum happened during a time when there were far less CO2 in the atmosphere than today.
Yeah.
So you are comparing two different states of the atmosphere, And people would argue that the fact that we have pumped quite a lot of CO2 in the atmosphere actually changes our current situation to the climate.
And we have answer within, we got answer actually a couple of days ago. Snow started falling in October.
Well,
Which we
So,
did.
and will be snowing much easier. So I can't say what I don't do, but I can provide you the link for this conference about temperature variation in Portugal, which happened early this autumn. And the people dedicated, they invented new method deriving temperature, and they're proving the temperature will not be that increasing even if there's no ground minimum. They will not be increasing. They're measuring many, like I got from media center of Finland. They send me the records. Their measurements show that their temperature is decreasing on the north. Also the measurements of Greece, the guys who do in plants, what they discovered last 2 years, the whole beginning of vegetation in the spring in plants becomes 1 month later. So the vegetables, the trees, they feel the reduction of magnetic field and they go into the conservation mode. So the nature is much better responding to what sun does than people, because people are attached to their own theory, to their own narrow view, and they don't want to hear anything around. I like my theory, and I'm going to get my Nobel Prize with it. This is what.
I'm sorry to go back to my question, but just to try and clarify it, your model doesn't take into account increasing CO2 emissions.
No. I do everything on the sun.
Indeed, it's wonderful. What impact will CO2 emissions have on your model?
None. I can answer none.
How-
Sun is so far away
Yeah.
that the Earth cannot affect
no,
it.
the question I think that
It means something.
the gentleman is asking is, do you think that the CO2 emissions have any effect on the warming
On the
trend,
terrestrial.
on the terrestrial warming trend we've seen over recent decades? Or
My
is this
personal opinion, I trust Murray Selby. I believe no. They cannot measure it. They cannot measure it because it is too small. It's only 3%, while the natural carbon CO2 is much higher.
Well, that's a slightly different question.
Yeah.
That's you're answering the question about whether it's human emissions that have caused the increase in the
So
atmospheric.
I don't believe it, but this is my
Ratio.
opinion. Again, it is like a religion, right, at the moment, because
It is a religion.
they never give you the instrument. I read it that the people who invented measuring CO2, which you cannot measure, they patented the instrument and do not give anyone who can use this instrument by other. The science is replicable. If it is correct science, I can do this, you can do this, you can do. I give you all the results. I explain you how you can repeat this data. You can repeat the same coefficients and everything. It's repeatable. If they do not allow to repeat, there is something dodgy about it. And so this is why I believe what Salvi and these people in Portugal say, that it cannot be happening because you cannot detect this small quantity. But I'm not specialist in the temperature. But I discovered with my own interest that I thought they immediately go and measure carbon CO2. But it turned out you can't measure it because it's heated into the evaporation. All this power station, they never put CO2. CO2 hidden in those clouds of water coming. So you need to extract somehow from there. How they do, he explains. But after you discover this one, that all the cycle CO2 is related to also exchange of water from all the surface to the sky and backwards. This makes things very complicated. This is one thing, but I am speaking what happening on the sun, and I'm speaking why solar irradiance will increase for the next 500 years without CO2, because of fluctuation of this baseline, because sun become closer to the northern hemisphere, it moves closer to apohelium for the next 500 years. So it does matter if it is humans, no humans, our temperature in the northern hemisphere in the summer will be increasing, in the winter will be decreasing. We will be having colder winter because sun moves further from perihelion. So this will be happening. And then after next 1,000 years, vice versa, this will be happening to the southern hemisphere. So this is what I can say from the sun point of view. So whatever adds to what sun produces is come from the climatologists, which I cannot argue because I don't do this research. But what I am saying, that even from the sun point of view, we discovered that solar system affect the sun, and sun moving either closer to Earth's northern hemisphere or further down. And its effect, and obviously we had this many thousand years on the Earth, as I said, mentioned Roman Empire. If you put backwards records, we had heats everywhere. So if you put records back, you discover we have them. Now we understand why we had them.
Keep it, please, as a question. We don't want any statements. We're not at a political conference, so please.
It's not a political conference.
No, please, a question.
Here's Corbyn Weather Action Long Range Forecasters. Professor Zharkova, what you've done is brilliant, and I will just say that everybody knows that here. And as regards the CO2 question, we're going to have a meeting on the 20th of December in the Royal Institution, where we've challenged the warmists to give us one scientific paper of evidence showing that CO2 real measurements actually drive temperature real measurements, and see what they come up with. Right, now, questions on this. You're saying the sun's a stable oscillator. Okay, well, the question is how stable? See, the point I would think that, and I agree with many of the points that Torberg says, question is the sun as stable an oscillator as the solar system is stable? In other words, if the solar system changed a bit, would the sun change a bit too? Now, I think it would.
No, we don't want your answer.
No, I know. I'm not going to go into
It should would. We discovered that Saturn, Neptune, and Jupiter affect the sun.
Can Professor Zharkova answer your question?
Yeah.
Right, but there's a supplemental
What
as
is
well.
the question?
Would you agree everyone involved in this has to be careful, as you say, to avoid assuming that they have the answer, because there are, I believe, many factors. You see, you correctly point out the oscillation in the baseline, which I think is brilliant, but you see, that is an external thing driven by planets, it would seem. And you haven't got anything in your 100,000 years data which shows the ice ages. So the ice ages are driven by something else as well, which is obliquity and precession.
Yes, but we didn't get planetary into it.
Which would you agree, those things modulate the receptiveness of the Earth to magnetic light.
We've got Piers, two questions
outside because you can get them on Google.
I'm sure
you can get Milankovitch cycles on Google, precession, and the migration, inclination. These are brilliant things. Actually, Milankovitch cycles inspired us to look. So if we couldn't find anything which can be on the sun responsible for this 2,100-year cycle, we couldn't find.
No.
Dynamo doesn't work. So you say, right, maybe I'm looking the wrong direction. So this is how we started looking. And it was Shirley and
Fairbridge.
Fairbridge.
Yeah.
Then 65, they first pointed out that, and then Sharbatova, she came up. But only they didn't accept people because they thought the whole solar activity done by the planets, and of course people thought, oh, this is crap. Solar activity cannot be done by the planets. What we were saying, of course not, it is not done by the planet, it affects probably only the upper layer, but it still affects the sun moves around the planet. So we put everything in perspective. We left what sun does, it is sun does. Solar dynamo stays there, stable, solid as a rock. But we still put some effect, which come from planets, from other planets, from Earth. from everything. So this is links us. So the theory, when they stop pretending that planets induce dynamo in the sun, dynamo people say, look, you're crazy, you go to madhouse, it cannot be, because the electromotive force will transform one poloidal field into toroidal and back toroidal to poloidal. It's very stable, they observe it on many other stars. So it is there, and no one can see that it's done by planets. In some stars they have dynamo and they don't have planetary system at all. So it does exist. This is why what we put now, we say you both right. You right, dynamo works, and you right, the planet work, but they only affect this baseline, and this is why we have variations.
No.
Follow on. Well, it's
Short.
It's very short.
Very short.
If you
Short.
could analyse, tell us what the omega values you get are, and can we relate those omega values to orbits of the planet?
You need to look at them. We didn't have this time. Again, to tell you what I did today, I had
Tell us the omega
lectures. I had
values.
lectures from 10 till 12. My students, I taught them waves. Then I took train, travel for 3 hours, go to hotel, jump, get taxi to get here to there. So this is my normal day. I do students, I do things. Only between the semesters I have little time to do. I have PhD student who need to finish his thesis. So yes, we could do this. But if the day would be not 24 hours, I would put Earth on the longer orbit. The day would be 48 hours. Then we could do this.
We'll take 2 more questions.
Brilliant work. Absolutely stunning. So good that I stood here the whole time because I came late. Presumably, we should be able to gather some kind of data off planet, in other words, on the other planets. There should be, as you mentioned in passing, there should be some way of deducing or measuring increasing and decreasing temperature on the other bodies, which wraps the whole thing because you can stop talking.
They are available.
Yes.
I didn't know about the IPCC in 2007. My partner is a local councillor. They asked me to give about climate change. And I did. I discovered the Mars ice melting, and Jupiter, because the temperature increased, they have typhoons which never had. So I said, look, we cannot do it. At that time it was Kyoto Agreement, not Paris. And I said, look, we cannot do this. Earth cannot impose this on Mars and Jupiter. So they do. They have much more data. But they do not listen. People from IPCC, they do not listen to arguments. They look on this way.
Last question. Gentlemen.
So I'm going to risk bowling out the political question, which concerns one of the bullet items you had on one of your slides. It was a bit scary to me because you were advocating intergovernmental cooperation to mitigate the adverse effects of the agricultural failures, which you say are quite likely. Now, we've already had one intergovernmental effort designed to save the world from climatological catastrophe. In view of that experience, do you really have any confidence that that is a good one?
I don't have confidence at all. What I'm saying, it would be nice if they put this from non-existent effect with a tiny, tiny amount. They put the whole world around with Al Gore, oh God, melting ices and everything. Yeah, this what. Why he didn't claim that they're melting on Mars, everything, so they did it. But this real thing, which will be happening, it will be happening with us. It will be happening like it was in March and April. You couldn't go, I couldn't start my gardening until after Easter, because it was wet, you can't walk, you can move the grass. But if you put the crops, you put potatoes, they're not growing. They had snow now in Spain, they put something. Everything they put is actually frozen out because they had snow, and it will be more snow. So they will realize in a couple of years or closer to the next minimum, they realize they have to do something. When there were snows in the March in the northern of America, the frost -20, I never had. There was rules here that our M62 was closed. You can't get to Manchester Airport because it's fully full. The cars were standing 24 hours because they could move. They standing there. So if we'll keep repeating this one, cars we can move, houses we can heat, we can, if not gas, we can go to the forest, we put these metal heaters, burjuika, we call them in Ukraine, and start putting, wood in there and heat your houses. So you can do some heating, but you can't produce the food unless you have greenhouses or you have storages. And it will be really essential at some stage. And this is what I'm saying. Of course, I don't believe they will be listening until it becomes freezing in June. When in June started snowing, they said, oh my God, this year we had June. What we do? We need to prepare for the next year. They start listening what will be happening next year. We're saying, oh, next year it will be even snowing in July, sorry. I can have you something easier. So this is when they need to think.
People blame on global warming.
Yeah, global warming because minus 20. It is interesting, isn't it? The people don't have logics. They can blame anything on global warming.
Professor Zharkova, many, many thanks. Let me finish our event tonight with two remarks. The first is, we will soon find out how good or how poor your research is, because
Absolutely.
you are putting it, you're not saying what was going to happen in 2100 or 2200, you're essentially saying we are facing a solar minima, this will have a direct effect on global temperatures, and they will decrease within a decade, will start decreasing. So that is fantastic, because this is testable. Observations will show how good your theory is. And that's how sound, and it doesn't actually matter. I mean, apart from the more catastrophistic predictions, it doesn't actually matter in science whether you're right or wrong. In science, it's all about doing your research, making a prediction, testing it. And if you fail, you will learn something. You will learn that something is perhaps not right in my model. Unfortunately, we don't have that culture anymore, which is why people like you find it difficult to even present your research.
Yeah.
And that's what we are about. We don't take a view whether your theory is right or wrong. We want to hear the whole spectrum of research, so that people can assess. I mean, we have to be aware that quite a number of Russian and Ukrainian astrophysicists in the past have made predictions about temperatures decreasing, and it didn't materialize, and they are, look with egg on their face, because they made these predictions and they haven't come true. I personally think it doesn't matter whether your prediction is right or wrong, because you're doing research and your focus is on understanding the sun, and there are so many things we still don't understand. And I hope, and I'm sure, your research will improve our understanding of the sun and its impact on terrestrial climate. So thank you very much.
You're welcome.